I'd like to start this off by saying that I actually wasn't supposed to do this project, and Miss Summers was probably right to tell me not to, because this happened. We set my deck on fire. But, it did happen, and I recorded it, and I didn't want to start over and make another cannon that was air-powered, so here we are. Combustion is a kind of chemical reaction, double replacement. You're going to take some sort of a fuel and an oxidant, and you're going to produce energy. With organic molecules, you're going to take some sort of a mixture of carbon, hydrogen, and oxygen. Add more oxygen, you'll get carbon dioxide, H2O, which is water, and you'll get heat, light, something like that if it's a rapid combustion. Because contrary to popular belief, not all combustion comes with an increase in temperature with like flames. You have rapid combustion and you have slow combustion. And with slow combustion, it can happen at lower temperatures. An example of this would be with respiration, where you are taking in oxygen, releasing carbon dioxide, but you're not releasing a whole lot of excess heat, but you are creating energy, so it's still usually considered a combustion reaction. With rapid combustion, which is what I'm going to be showing an example of today, you're always going to have heat or light going with it. Of course, we all learned about these sort of reactions this year already in class. They look something like this. In this specific example, you have carbon and hydrogen in some sort of a compound reacting with the oxygen gas to produce carbon dioxide and H2O, which come off from the fire and smoke, in addition to producing a change in heat, which we all know comes when you have flame. One thing that I think is really cool with specifically using wood as a fuel is while the wood is burning, the wood itself is not the fuel, it's gases that are released from the wood when it's heated, which I think is really interesting. These are really easy to identify. I mean, we had to do it for our test this year, but I want to go a little bit more in depth with that to show what's sort of actually happening, and as opposed to just what letters and numbers are getting moved around. So obviously, in order to do an experiment where you use an alcohol cannon, you have to actually build an alcohol cannon. So I went down to Lowe's and I bought some PVC pipe and stuff. I followed this video that I found on the internet of a chemistry teacher doing it, and I got some giant foam dice from Walmart and I cut them up to fit into the pipe. I'd show you all of the filming that I did of making the cannon, but to be honest, I kind of sucked at using the drill, and I'd rather not embarrass myself like that, especially since I just got put as captain of the robotics team. They might kick me out. So I'll show you a couple of seconds of that, but I'm not going to subject myself to that embarrassment for too long. Just say that it did happen, and it was built. The first time that I did this, the cube didn't actually really go that far, but we got better at it as we went on. We were able to get it to go farther. One time it didn't exit, you'll see that, but I'm just gonna let you watch some of the clips of this. Have a fun thing, or whatever else you want to do.
Projectile.
Projectile, we'll call it projectile.
Loading.
Have our incredibly leaky
Propellant.
propellant. Three good spritzes. Always good to hold flame when your hands are coated in alcohol. That's so good.
Yay.
Yay.
Sorry.
Alright.
Accidental selfie.
Oh, sweet goodness gracious, that was a lot of gas in my face. In the words of the ever-wise Cameron Homer, this is probably gonna blow up. We added some canola oil to grease the inside, and we're pumping it up with some air, in addition to the denatured alcohol we've been using for the majority of these.
That's
to help the alcohol vaporize. Where did it go?
I don't know where that went.
Where did it go?
Actually still in there.
Wow. That was a heck of an explosion for him not going anywhere.
I don't know if you could actually see in there or not, but he is in fact still in there and probably very charred. Yeah.
Alman Sukubaran is calling you or something like that. Yeah.
Oh, that's not a good sign. Nice. Look at for robotics.
Hold on. Ugh.
Ah, didn't email that fifth grade teacher. Okay, you know what? That's not important.
Hold on. Okay.
Woo!
Wow.
Yeet!
There were flames coming out the back.
Please ignore the trash. My mother would be ashamed. But she's watching soap operas right now, so she can't judge me. Yeah. We're ready. Yeet! So since I'm like really over on time for this video and Miss Summers is already kind of upset with me for this project, and because I've been working on editing this for like 4 hours now, we're gonna go through the specific chemistry of this exact combustion equation pretty quickly. So my fuel in this was denatured alcohol, which is ethanol that's been combined with poisonous substances that make it either look less clear, which not in this case, but poisonous, you know, things that'll make it less likely that someone would want to eat it. Ethanol is usually placed in a water-type solution. The more alcohol that you have in it, the more flammable it is. If it were 100% ethanol, this would have ignited at 61.88 degrees Fahrenheit, which is less than room temperature. So that's a very low flash point. Flash point being when it ignites, when an ignition source is applied. So I'm not sure exactly what the percentages on this one were. They didn't really say on the label. But so you take the ethanol, you combine it with, we applied a lighter, so we were using already a flame combustion to create another combustion. And that combines with the oxygen that's in the chamber, and it forces the cube out because of the buildup of pressure that happens along with the heat and the light. So that's what happens there. The more completely the reaction occurs, the farther that the cube would go. Sometimes the alcohol wouldn't be able to react completely because there wasn't enough oxygen in the tube, and you'd have leftover alcohol and it wouldn't go as far. So that's how that went down. I'm going to combine two of the things that I mentioned, flash point and the gas particles that I mentioned earlier with the wood. So the flash point is when you reach the activation energy that you need to start the reaction, and that activation energy is determined by how difficult it is to get the molecules in a fuel to enter that gas phase that I was talking about with the wood. And so obviously the difficulty of separating them has to do with the strength of the chemical bond, which is something we've learned a lot about this year, different depending on if it's ionic, covalent, or how the structure of the compound is determines how closely knit they are, the state of matter. There's a lot of things that go into it. And like the coolest thing with all of this is just realizing that flame is not its own individual thing that is in a state of matter. That's you seeing your fuel rapidly oxidizing and releasing light. And that is the chemistry of combustion.